Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So this is another video from the Strivers A to Z DSA course. Just in case you're for the first time here, this is world's most in-depth course on DS Algo. Why do I say that? You can go across internet, you can buy any of the paid courses. None of them will be covering DS Algo in such depth. We will be covering 456 modules and we will be solving 400 plus problems in this DS Algo course. So when you end this course, you can actually clear any of the DS Algo rounds in any of the interviews in any part of the world. So till now we have covered till step 3.1 fourth problem, and in this video we will be covering these 5 problems. Just in case you wanna directly jump to any of the particular problem, the timestamps will be there. You can directly jump over. But let's get started with the first problem, which is left rotate an array by one place. So if you have seen our previous video, you know that we always start from brute, then we go to better, and then we go to optimal. Given that the brute and better exists for that problem, and this is the way you should always tell in an interview. Why? Because in an interview, your thought process should be visible to the interviewer because it's you who will be driving the interview. So make sure you follow this particular step by step optimization of approaches because it does leave a very positive impact on the interview. Now, coming back to the problem, left rotate the array by one place. What does it mean? So, given an array, you have to left rotate it. Yes, you have to left rotate it by one place. So, if I have this array and you have to left rotate it by one place, so one place. So, one element will go and rotate it. So, basically, this one will go to the end because you rotate it, and everyone will move a bit because you are rotating it. So, it will be like 2, 3, 4, 5. So this is what rotation means if I'm talking about left rotation. So I have rotated the array and this will be my final array. Now for this problem, this is a very easy problem. So you can directly jump to the optimal solution instead of going like to the brute where you take another array and store the answer in another array. It's not required. For this problem, you have to solve the problem in the given array itself. Like you cannot use any new array. Make sure you solve the problem in the given array itself. Now, since it has been clearly stated that you have to just rotate it by one place, hence the problem is very simple. After that, we will be increasing the difficulty of the problem. But as of now, let's understand how do you left rotate by one place. Now, I know one thing. If I have to talk about left rotation, let's visualize what happened in the final array. In the final array, this is the only guy that went to the last. The first guy is the only guy that went to the last. And apart from that, what happened? The 2 moved here, the 3 moved here, the 4 moved here, the 5 moved here. So it's like they moved one place, ahead. So moving them one place ahead should not be a big deal. But we need to store this one. So assume I say temporary equal to array of 0. And over here, temporary will be stored as 1 because array of 0 is 1. Now, what I say is, okay, I'm standing here. This 2, ideally, since it is left rotated by 1, should go at the 0th index. So I'll place it here. So it's like saying, okay, if I'm at ith index, I'll place it at 1 index before. And then again, I'll move the ith index and I'll see, place it at 1 index before, which is again the I minus 1. And then again, I'll move the ith index and I'll say, place it at 1 index before. So this will be placed here. Then I'll move here and I'll say, place this 5 at 1 index before. So this will be placed. Once I've done this, the iteration will be over. Once the iteration is over, the last place is having 5 as of now. We need to take this one and place it at the last place. And the 1 is stored in temporary variable. So you take this temporary and put it into the last index. So this will take 1. Hence the array will get modified to this after left rotating it by one place. Now let's talk about the implementation. How will you implement it? Can I say this is nothing but the first index and this is nothing but the n minus 1th index. So thereby what you can do is you can say for I, like at first what you can do is you can always store temporary of array of 0. And then you can start from 1 and you can go until n minus 1. So you can run a loop till n minus 1. And then you can say this ith guy will go to I minus 1. So array of I minus 1 will store array of I. Once this loop is completed, that means this will be completed. And at the end of the day, at this position, which is nothing but array of n minus 1, whatever we stored in temporary, we take it and we will place it over here. As simple as that. If I have to discuss the time complexity, what will be the time complexity? Yes, a simple bgo of n pass, because we are running this loop for n times. Thereby, the time complexity is bgo of n. Are we using any extra space? No. Thereby, the space complexity is bgo of 1. Why? Because we are doing everything in the given array itself. So we can say that we are not using any extra space. But yes, we are modifying the array. So the space used to solve the problem is bgo of n, because we're using an array to solve the problem. Yeah, that array is already there, but we're using it. So if someone says, what is the space used in your algorithm? Then it becomes big of n, because you definitely are using this array, but it is already created, but you're using it in your algorithm. But if someone says, what is the space that you're like, what is the extra space that you're using? Then the extra space is big of 1. But in for the algorithm, we definitely are using this. So understand the subtle difference. If someone says in the algorithm, you should always take the space that you are being used, like that's being used. And if someone says, what's the extra space? Then you can say big of 1. So there's a subtle difference. Whenever you go to an interview, always clarify it. Tell them that, sir, the extra spaces. So whenever you go to an interview, always clarify this. Tell them, sir or ma'am, the extra space that I'm using is big of 1. But in order to solve this problem, I'm using this array. So if you have to take space into consideration for the algorithm particularly, I will say I'm using this array. So thereby a big of n space is being used. Yes, it's already given to me, but I'm using it in order to solve it. So this way you tell to the interviewer, so that every concept of yours is crystal clearly presented to the interviewer and he is impressed. This is how you should drive the interviews. Got it? So if you want to solve this problem, the problem link will be in the description. So I've written the exact same code and I'm submitting this problem and it is running absolutely fine. So I've solved this problem. Now, if this problem comes up in an interview, the follow-up question very likely will be the next one, which is left rotating an array by d places. Till now, you have solved a problem where you did left rotate the array by one place. Now, I am telling you, okay, one is easy. What if I give you two? What if I give you three? What if I give you four? Can you left rotate an array by certain number of places? So that certain number is d. D can be anything in a problem. So you have to design an algorithm so that the algorithm works for any given number of places. That is what the follow-up question will be. So let's try to solve this follow-up problem. So let's understand the problem statement. It states you to left rotate the array, but this time by d places. Assume for this given example array, we have d equal to 2. So it's stating that left rotated by two places. So these two elements should be left rotated, and these elements should be moved by two places. This is what you mean by left rotation. So if I do that, the resultant array will be 3, 4, 5, 6, 7, and then 1 and 2. So this 1 and 2 kind of moves here and then moves here, and these will move two places ahead. So this is what the resultant array will be after you have left rotated the array by d places. D over here is 2. D could have been 3. Yes, D could have been 3 as well. In case of 3, what would have been the answer? Yes, obviously. In that case, 1, 2, 3 would have been left rotated and they would have been moving by 3 places ahead. So in that case, the answer would have been 4, 5, 6, 7, and then 1, 2, 3. So that's the answer for D equal to 3. Now, what if? Yes, what if, like, let's count the size of the array. It's like 1, sorry, my bad. 1, 2, 3, 4, 5, 6, 7. 7 is the size of the array. Imagine I asked you, can you rotate this? Yes, can you rotate this by 7 places? So if you actually rotate this by 7 places, it will again come back to the same place. It will again come back to the same place. So rotating it by 7 places will bring it back to the same place. So if I ask you, can I rotate it by 8 places? If you do a rotation by 8 places, can I break 8 down to 7 rotations plus 1 rotation? Can I? I can. So can I see that? Hey, listen, on 7 rotation, it comes back to the original array. And then you just have to do one rotation on it. Make sense? So if it is 9 rotation, can I break it down to 7 plus 2 and say, okay, on 7 rotation, it will be the original array again. And then you just have to do a meager 2 rotation on the array. Does make sense? If I tell you d equal to 15, can I write 15 as 7 plus 7 plus 1? Stating that on two 7 rotations, the array will be back to its original. And then you just have to do one rotation. And that will sum up to 15 rotations. So can I say multiple of 7 rotations can be done? And it will always bring you back to the original array. I repeat, multiple of 7 rotations will always bring you to the original array. The remaining is what you need to do. So can I say whatever array is given to you, whatever d is given to you doesn't matter. The number of rotations you have to do will always be d modular whatever is the size of the array. Can I say this? If it's given like 20, doesn't matter. I'll just have to do 6 rotations because 20 modulo 7 will be 6, which means you have to do 7 2 times and the remaining 6. So you actually have to just do 6 rotations. And if you have any number of rotations which is lesser than the size of the array, it's very simple. If I say 6, it means this will go here. It's like 1, 2, 3, 4, 5, 6, and this will go here. That is the meaning of 6 rotations. So anything lesser than 7 is very easy to solve. That's why we will always do a modular of n, because n rotations, like on multiple of n rotation, means coming back to the original array, which we do not care. We care about doing the next set of steps. Got it? So that's the first thing we have to be careful about. Whatever d is given to you, just do a modulo with n and that will be solving your problem. And that will be solving your problem if d is very, very large. So if in an interview this question comes up, the first approach that you'll be telling will be the brute force approach. Now, what will be the brute force approach over here? Let's go back to the previous problem. In the previous problem, d was one element. Yep, you were being asked to rotate the array by one place. So you initially took a temporary and you stored one element. This one element was stored. And then you did this. And then you replace that one element to the last. We'll do the exact same thing. D was 1 over here. So you stored one element. If D is 2, you will be storing 2 elements into this temporary. And then you will rotate. And then you'll take the 2 element and you'll put it on the back. That's what we will do. Let me explain. So what I'll say is, okay, D is 3. So I'll take a temporary array or a temporary list, whatever you can. And I'll say, okay, let's take the first 3 elements. Very simple. Done. So I've taken the first 3. And I've put that into the temporary array. Similar to what we did in the first problem. Now, what was the next step? Shifting. So let's do the next job of shifting. Now, when I say shifting, how will you shift? Let's write down the indexes and let's try to observe how do we shift. So if I write down the indexes, it's like 0, 1, 2, 3, 4, 5, 6. And if D is 3, we start shifting from third index. We start shifting from the third index, which is the dth index. So we start from here. And where do we put 3? Let's analyze. 3 is put to the 0th index. Obviously, 4 will come here. And the 4th index is put to the first index. This one will come here. And then the 5th index, which is 6, is put here. So 5th index comes to 2nd. Do you see where it is coming up? If this is your ith index, it's always coming to I minus d place. This is where it is coming to. The shifting is happening in this way. So what I can say is, okay, for shifting, I can probably start from this one, which is the third index, which is nothing but d. And I can go until the last, I plus plus. And I can say array of, because the third index guy will go to the 0th index guy. Please observe, this guy goes here. and this will become 4. So it goes 3 places back. It goes d places back. So I minus d places is where the array of I will go. So once you have performed this shifting, how will the array look like? Let's write. Once you perform this shifting, how will the array look like? It will look like 4 is here, 5 is here, 6 is here, 7 is here. Now you still have 3 places where 5, 6, 7 is there. And what do you need to put it? Like, what do you need to put there? Very simple. You have to take this temporary and you have to put the temporary one by one here, which is like 1, 2, 3. Quite simple. So put back temporary is the last step. Put back temp is your last step. So let's put back the temp. So I can say, how do I put back the temp? Now we need to analyze. Where are we putting it? Let's try to analyze. So can I say, if we are shifting by 3 places, it means if the size of the array is 7, 3 places before it, because the last 3 places will only be occupied if we are shifting the array by 3 places. Only the last 3 places will be occupied. So I'll be like, okay, 7 minus 3, which is basically n minus d, which is basically 7 minus 3, which is basically 4. So we're starting at 4. Can I say we will start putting at the 4th index? Can I? I can. So I'll start putting it from the 4th in like n minus k, and I'll go on to the last. Quite simple. And what will we put in the array of I? What will we put? We'll put first 1. So we'll put something from the temporary. We will put something from the temporary for sure. Now we need to figure out what's the index. The easiest way to do this is like without any mathematical calculations or anything. The easiest way is say j equal to 0 and put j and then do a j plus plus. So what will happen? At first j is here because that's the 0th index. Takes up 1, puts it here. Then j goes here, takes up 2, puts up here. Then j goes here, takes up 3 and puts in here. So you put j and you increment j. You put j, you increment j. And this will easily fill up the last 3 places. That's one of the ways to do it. But if you're going to an interview, you have to show all your skills. So this is the first thing you'll tell in an interview. Then you can say, maybe we can get rid of this possible j. Yes, let's get rid of this possible j. Can I deduce something which is mathematically correct? I can, maybe. So something which I know is this element, which is at the 0th index, will always go to the n minus dth index. Can I say this? I can. Now, can I say someone who is at the first index will always go to n minus d plus 1, which is basically the next index? I can. Now, can I say someone who is here will always go to here, which is apparently 2 places ahead, which is n minus d plus 2. Can I say this? And this is the second index. So n minus d plus 2. So can I say if your base index is n minus d is your base index. Can I say this? The temporary will say, okay, if you are standing here, if you're standing at I, then you just need, n minus d to get your base index. Can I say this? You just need I minus n minus d, because again, I'll repeat, this is n minus d plus 2 and this is n minus d. So if you are trying to put something here, then if you just subtract this, you'll get 2 and you can get the second guy from here. Quite simple maths. Very, very simple. Take a pen and paper and try to do it yourself. I'll repeat again. The base index here is n minus d. Then the next index will definitely n minus d plus 1. The next will be n minus d plus 2. Right? And we're taking from 0, 1, 2. So this is like 0. This is like 1. And this is like 2. That's why wherever you are currently at, just subtract the base index. If you subtract, first you'll get 0, then you'll get 1, then you'll get 2, which apparently means this. So you'll automatically take the temporary. So this is how you can easily put it back. Got it? So quite simple. First I stored everything from the temporary. Again, to store everything from the temporary, you just need to loop from 0 to d. So it's like looping from I equal to 0, I lesser than d, and I plus plus. And in the list, you can probably take a vector or a list in Java. Push back in Java, it will be list.add. array of I. That's it. So this is the putting into the temporary. This is the step one. So this is how you can put everything over there. Then you can easily shift, and then you can easily put back the temporary array. This is how you can easily do it. So for this brute approach, I have written the pseudocode so that you can code in C++ or Java. But coming to a cleaner code, we just take the array as the input, and then we take the D, and then we call the left rotate function which rotates it, and then we just like print it. So let's look at the function. So it takes an array, it takes the size of the array, takes D, and the first step we make sure is we just reduce the D to something lesser than n, because we know on all the multiples of n it will come back to its original array, and then we store everything into temporary, then we shift it, and after that we place back temporary into array. Quite simple. So that was the cleaner code, and the problem link will be in the description. So what will be the time complexity? So can I say the time complexity will be, in order to do the step one, this is taking up big O of D, because we are looping through the first D elements. Next, can I say in order to transfer, like shift everything, that's going to take big O of n minus D, because those many elements are what you will be transferring or shifting to the front. So n minus D. The next one, putting back temporary. So that's like again big O of D, because you're putting back D elements. So that's like big O of D. And if I have to add it up, it will become big O of n plus D. This will be the time complexity. And if I ask you what is the very important word, what is the extra space used? Extra. So the extra space used will be big O of D. Why? Because you are using a temporary array to store the extra elements. Now this is where the interviewer will tell you, okay, fine enough, but I want to get rid of this extra space. Can you just do it and big O of one extra space? That's when you'll say, okay, maybe I'll try to optimize this into an optimal solution. For this, a better might not exist, so I'll not discuss it. But this is where I'll try to optimize this into an optimal one. So let's look at the optimal solution. So let's talk about the most optimal solution. The most optimal solution will be based on observation. Now this will be the resultant array after you have rotated this array by 3 places. Now something to observe. This 1, 2, 3, yes, this 1, 2, 3 is over here. Okay. And this 4, 5, 6, 7 is over here. So what we can do is we will say, okay, let's take the first 3 elements and try to rotate it. So I try to reverse it. So if I reverse it, it will be 3, 2, 1. I've reversed it. And then I'll say, let's take the last 4 elements. Let's try to reverse it as well. So if I reverse it, it will be 7, 6, 5, 4. Now what I'll say is, okay, this is the reversed array post 2 reversal. One is the first D, the next is the n minus D elements. After this, if you have to get this final array, what do you need to do? Reverse it again. So if you reverse it, what will happen? This 4 will come first, this 5 will come here, this 6 will come here, this 7 will come here, this 1 will come here, this 2 will come here, and this 3 will come here. Done and dusted. Yes, this was super easy. So I will say reverse first array to array plus D. Then I'll say reverse from array plus D to array plus N, which is the last one. And then I'll say reverse the entire array, which is array to array plus N. So if I perform this 3 reversals, I will actually get the resultant array. I don't have to take a temporary, do shiftings, and then copy pasting back again. Just 3 reversals. First for the D elements, then from D to N, and then the entire array. And if I do this, I should be done. And this will take me a big O of D complexity, because we are reversing D elements. This will take me a big O of N minus D, because we are reversing N minus D elements. This will take me a big O of N, because we are reversing the entire array. So overall the complexity will be this plus this. So D and D will strike out, and the complexity will be 2n. So the time complexity slightly increased from the previous one. But the space complexity, we are not using any extra space. Very important. We're not using any extra space. Yes, we are using the array that you can tell to the interviewer, but we are not using anything extra. We're using the given array. Okay, that's why the space complexity over here will be VCO of 1. Got it? So let's quickly code this up. Again, the problem link will be in the description. So there is a reverse function in C++. So if we just give this, it will reverse from array plus 0, like 0th index, to d minus 1, to d minus 1. And then you can say again reverse array plus d to array plus 1. This means from dth index to n minus 1th index. Then I can say again reverse array plus, plus 0. That means from 0th index to the last index. If we do this 3 steps, it will be done. And now I can quickly run this and see if it is running. Yes, and now we'll submit this. I should be submitted. So in case your programming language does not have a reverse function, you can always write something like this, which is a manual function where you take the starting index and the ending index, which means you want to reverse from this index to this index. And this is quite simple. You can go through this. It's very, very simple. And this will also work like if you write a manual function. Just because in C++ there is an STL, that's why I did not write an extra function. But in an interview, the interviewer might ask you to write an additional function without using the STL. So in that case, you can go ahead and write a similar function which will reverse you a particular array from start to end. So with this, we are done with this problem as well, which is left rotate an array by d places. Now remember, there might be a follow-up question to this in an interview, which is, what if instead of left rotation, I'll say you right rotate the array by d places? Then you have to come up with a solution. And this will be an assignment. Try to think how will you right rotate an array by d places. And once you have written the code, you can put that into the comment section. Also remember, in an interview, do not jump to the optimal solution directly. Go from brute to optimal. That will show your thought process, and that does leave a very, very good impact in the interviewer's head about you. Okay, let's now move on to the next problem, which is moving zeros to the end. So what does the problem state? Move all zeros to the end of the array. So you will be given an array which will be consisting of some integers, and it will also be consisting of some zeros. Now your task is to move all the zeros to the end of the array. So first there will be 1, then there will be 2, then there will be 3, then there will be 2, then there will be 4, then there will be 5, then there will be 1. So basically what you do is you take 1, 2, 3, 2, 4, 5, 1. So I took all the non-zero numbers and I put them into the front of the array. Once I've done that, what are the remaining elements? There are zeros and there are 3 zeros. So you take all the 3 zeros and you put it to the end of the array, right? So once you've done this, the modified array will look something like this. And this is what the problem is asking you to do. Question is asked to you in an interview. You should definitely start with the brute force solution and then maybe come up with a better solution if there is one, and then go to the optimal one. So what is the brute force solution? If you look at the problem, it states all the non-zero numbers at the front, like all the non-zero numbers at the front. So my mind kind of says that, okay, let's pick up all the non-zero numbers and store it somewhere. So what I'll do is I'll start iterating in the array. So I'll start from the first index and I'll say it's a non-zero. Let's pick it up. Then I'll go to the next, it's 0. Then I'll go to the next, it's a non-zero. Then I go to the next, it's a non-zero. It's a non-zero. It's a 0. It's a 0. It's a non-zero. It's a non-zero. It's a non-zero. And the iteration is over. Once the iteration is over, I can say that I have all the non-zero numbers. And again, you can store them in a list, in an array, wherever you wish to. So I have all the non-zero numbers stored with me. Once I've done this, what is my next job? I know one thing for sure. I have all the non-zero numbers that will go at the front. So let's do it. Let's assume this is the temporary array. Let's take everything. Let's first take 1 and put it here. Let's then take 2, put it here. Let's then take 3, put it here. Let's then take 2, put it here. Let's then take 4, put it here. Then take 5, put it here. Then take 1, put it here. So I have taken everything from the temporary array and put them into the front of the array. Once I have done that, I know all the non-zero numbers are at the front. If I've done that, what is the next job? All the remaining positions will definitely be zeros. So I'll just assign them zeros. Done. And this is how my brute force approach will look like. First iterate, store all the non-zero numbers. Then put all the non-zero numbers to the front and then fill the remaining places with 0. So if I have to code this, what I'll do is I'll probably define a temporary, which is an empty list, and then I'll start iterating from the 0th index until the nth index. And I will say, hey, listen, if you are a non-zero number, which means not equal to 0, then can you go and get added to the temporary, and you'll add it to the temporary. Simple. This will create your temporary array with all the non-zero numbers. So I can say the step 1, the brute force approach is done. What is the step 2? Step 2 is very simple. Pick up everything from the temporary and put it into the front of the array. So you will just move in the temporary array. So I equal to 0, and then you can go to temporary dot size, because that will tell you how many non-zero numbers are there, and then you can move. And you can say array of I, let's put it into the front. Array of I equal to temporary of I. So this is step 2. Once you've done the step 2, all the non-zero numbers will go to the front. Now the step 3 is filling up of zeros at the back. So I know if temporary dot size like is the number of non-zero numbers. Like over here, it is like 1, 2, 3, 4, 5, 6, 7. So it took the first 7 places. So the last index it took was the 6th index. So you'll start filling from the 7th index, go to the 8th, and go to the last, which is the n minus 1th index. So you start filling from the 7th index, which is nothing but number of non-zero elements. So you'll just start from the non-zero elements, like whatever it is, the number of non-zero elements, and you'll go till the last, and you will say in all of these places I'll just fill up 0, and this is how my brute force will look like. And if I have to analyze the time complexity, can I say this is taking a big O of n because I'm running an entire loop? Can I say this will be taking, imagine there are x non-zero numbers, so this will take x, and this will be the remaining portions. So the remaining portions will be n minus x, because if x is the number of non-zero, the remaining will be n minus x. So can I say the total time complexity to be big O of n plus big O of x plus big O of n minus x? So minus x plus x will cancel, and that will be big O of 2n will be the time complexity of this particular one. And can I say the extra space, again very important, the extra space that I'm using will be big O of x, where x is the number of non-zero numbers, and that at max can be big O of n. Imagine the entire array to not have a single 0. Then you'll end up transferring the entire array into the temporary array. So thereby this is the worst case. So thereby this is the worst case where there is no 0 in an array. Then you will transfer the entire array into the temporary. So that in that case you'll be using big O of n space. So this will be the time complexity and space complexity for the brute force solution. So in case you want to code the brute force solution and submit it, the problem link will be in the description. There is a reason why I'm writing the pseudocode so that you can code it in any of the languages. But still, if you want the Java and the Python codes, the link will be in the description. You can go to the notes and you can check them out. So the brute force solution is done. Now it's time to move to the better solution, but there is no better solution. So we'll be moving to the optimal solution. Now this is what you have to tell to the interviewer. What will be an optimal solution? Let's analyze the thought process. Till now, what we did was very basic. We just picked up the elements and put them into the front. But now we'll try to do it on like while iterating. How can we do that? If somehow I can take this 2 and put it here, and somehow I can take this 3 and put it here, somehow I can take this 2 and put it here, and maybe somehow I can take this 4 and kind of put it here, my job should be done. So we'll be trying to move the elements. We will be trying to move the elements. And in order to do that, we're already iterating in the array. Remember this, we're already iterating in the array. So what we will do is, we'll try to use a 2-pointer approach to move it. Something similar to what we did in this particular problem where we did remove the duplicates from the sorted array. Something similar. Now what I will say is, okay, hey, where's the first 0? And I'll say, here is my first 0. And this will be pointed by j, which is the right next index after 0, which is this. I'll point it over here. Now what I say is, hey, listen, I start from here and I check, are you a non-zero number? He says, yes, I am a non-zero number. Okay, we have a 0 here. Let's swap it. So I'll do a swap. So the 2 will go here and the 0 will come here. The moment you have done a swap, you will say, okay, done. Now I'll move to here and I'll also move the j to here. So once I've moved, I'll just quickly erase this so that it's clearly like it's clean. Done this. Next, I'll say, hey, are you a non-zero number? He says, yes, I'm a non-zero number. I'll say, okay, swap to the 0. So I'll go across and again swap. So 3 goes here, 0 comes here. And the moment you do that, I will move ahead and j will move to the next place. And if you've done this, let's remove this so that it's again clean. Next, are you a non-zero number? He says, yes, I'm a non-zero number. I'm like, okay, swap. So 2 goes here, 0 goes here. Perfect. And now I'll move I here and I'll move j here. So j will be always at a 0. J will be always at a 0 and I will be simply iterating. Okay, next. I ask, is this a non-zero number? He says, no. So no swapping. I moves. Is this a non-zero number? No. No swapping. I moves. Is this a non-zero number? He says, yes, I am a non-zero number. So I'm saying, you're a non-zero number. Okay, you need to go to the 0th gap. So he says, okay, I'll go. So I'll go to here, which is 4, and this will be 0. Perfect. And the j will be moving here, and the I will be moving here. Once I've done this, I'll just clean this. Next, 5, are you a non-zero number? He says, yes. And 0 comes in here. And then I move I here, and then I move j here. Next, 1, are you a non-zero number? He says, yes. So 1 comes here, 0 goes here, and I crosses the boundary. The moment I crosses the boundary, you stop. And do you notice something? All of these positive, like all of these non-zero elements are in the front, and all these zeros went to the last. Very simple. And it's done. And what we did was a single iteration. If you carefully observe, what we did was we started the iteration, like we first figured out the 0, and then we started the iteration and we went till the end. So it's like a one iteration we did, which is much better than what we were doing previously, right? So in the optimal solution, what is my step 1? If I have to ask you, what is my step 1? It's finding the first 0th element. So what you can do is, you can probably say j is initially -1. Okay, and then you can start from 0 and you can go on till I++. And you say, hey, array of I, are you 0? If you're 0, okay, fine. J, store this index because this is 0 and just go out. No need to go ahead, go out. And this will make sure J is stored as the first, like wherever the first 0 is. If J is still -1, it means there is nothing and you can just stop. You can just stop. If J is still -1, there is no 0 and all are non-zero elements, so you can stop. The moment you have J, what's the next step we did? We took a I right at the next of J. And this is where we start out. So I said, okay, I'll start from J plus 1 and I'll go until here. And what did we do? We said, hey, are you a non-zero? Are you a non-zero? He said, yes, I am. So I'll check, hey, if array of I, are you a non-zero number? If you are a non-zero number, can you please swap yourself with array of I and array of J? And if you have swapped, can you just move your J++ pointer? Because I will always be moving no matter what you do. But the moment you get a non-zero number, you just swap it and then you move J as well. But whenever I was here and it was a 0, you did not do anything. It's just the I always moved. I always moved because J will still stay where it is. So J swaps and then moves ahead. Quite simple step 2. So the step 2 is also done. So if I have to figure out the time complexity, can I do it now? I think I can. First, we moved till here, assuming this to be x. Assuming this to be x length, where the first 0 was found. So the step 1 takes you big O of x because you're doing a break, where x is the first index where the 0 was found. Then you move from here to here, which is the remaining n minus x length. So this is like the remaining n minus x where you moved. So the overall complexity is this plus this where x and x goes off. So the time complexity overall is big of 1. Sorry, big of n. Are we using any extra space? No, we're using the given array. Yeah, we have to tell that to the interviewer that, hey, listen, I'm modifying the array because that's required. But we're not using anything extra. We're not using anything out of the box. So this will be the time complexity and space complexity of the most optimal approach that you have to tell to the interviewer. So if you want to submit the optimal solution, the problem link will be in the description. What I've done is I've converted the same pseudocode into a C++ code just in case you want the Java and Python codes. The link will be in the description for notes. You can go over there and check it out and you can try submitting it as well. I'm focusing on the pseudocode so that you can write it in any programming language. Remember this. So coming back to the sheet, I can say that this problem is done. Now the next problem that we will be solving is linear search. Linear search is one of the easier problems while it comes to arrays. It just involves iteration. If you understand iteration in an array, you should be able to solve linear search. Now what does linear search say? It says that you'll be given an array of numbers, and you will also be given a separate number. Now you have to tell me which is the first occurrence, very important, which is the first occurrence of this number in an array. So if I have to check, this is where the number occurs. What is the zero-based indexing? Again, very important. What is the zero-based indexing? So the zero-based indexing is 3. So you have to return 3. Yes, you have to return 3, which means it like the number does exist in the third index. If I give you something like 10, what if the number is 10? If I scroll through the entire array, like if I look at the entire array, the number 10 doesn't exist. That's when you return -1. Simple, right? Very simple. How will you solve this? Yes, quick iteration on the array and check. That's like, I'll just go across the array. You know how to iterate in the array now. You just go across and you say, hey, listen, if at any moment array of I is equal to the number, I will try returning the ith index because that's where the first occurrence is. If they want last occurrence, you start iterating from the last. If they want all occurrence, then you can always store this I in some temporary array or some list. And at the end of the day, you can say return -1, which means I did not find it. If there is a complete iteration done and the return statement was never ever executed, then you will go across and return -1. Now going to the compiler, again, the problem link will be in the description in case you want to try it out. And this is how the code will look like. And again, the Java and the Python code will be given in the notes so you can check them out as well. So with this, the most easiest problem in the array playlist is done as well. And now let's go to the next problem, which is finding the union and the intersection of two given sorted arrays. So what is the problem statement? Union of two sorted. Again, very, very important word because this will be helping us to determine the most optimal solution. So union of two sorted arrays. So this is array 1, which is sorted in itself, might have duplicates. Array 2 sorted in itself, again, might have duplicates. So what you have to do is, you have to give me an union array. What is the meaning of union? So what do you mean by union? It's basically you're given two guys and you just add them up. But you do not repeat anyone. You do not repeat anyone. It's like if you have 1, okay, 1 goes. You have 2, 2 goes. You have 3, 3 goes. You have 4, 4 goes. You have 5, 5 goes. Then you start from here. You have 2, but wait. 2 is already here, doesn't goes. 3 is already here, doesn't goes. 4 is already here, doesn't goes. 4 is already here, doesn't goes. 5 is already here, does not goes. So this is how you can easily do an union. So the union of the both arrays will be 1, 2, 3, 4, 5. Imagine I just go ahead and say, hey, listen, I also have a 6. In that case, the union will be 1, 2, 3, 4, 5, and 6. Quite simple. Because 6 is over here. It's not here, but it's okay. You have to add both of them. You have to add both of them. And make sure there is no duplicates. So this will be the answer for union of two sorted arrays. And this is what you have to return. So this problem comes up in an interview. The first solution that you'll be telling the interviewers should be the brute force approach. What will be the brute force approach? What are we doing? We're combining both of them. But we are making sure the unique elements are just there in the union array. So whenever we hear something like unique, something like a map or like a set comes to our head. Because if we just keep on throwing everyone to the set, at the end of the day, the set will only contain unique elements in a sorted order. In a sorted order, very important, because you have to return the union in sorted order as well. So can I say, let's take a set data structure. I'll be like, why not? Let's take a set data structure. So assume this is my set data structure, which is as of now empty. I'll start iterating in the first array. 1. Put that into the set. 1 again. No. 2 goes into the set. 3 goes into the set. 4 goes into the set. 5 goes into the set. Perfect. Iterate in the second array. 2 already in the set. If you try to put it into the set will say, I already have it. 3 already in the set will say, I already have it. 4 already in the set. 4 already in the set. 5 already in the set. 6 not in the set. So after iterating in both the arrays, the set data structure will have 1, 2, 3, 4, 5, 6. And now what you can do is, you can probably take a union array, and in that array, the size of that array will be nothing but the size of the set, which is 6. And you can just pick up one element, pick up 1, pick up 2, and put them into the array, and put them into the array. That's what it will be. That's how it will look like. Once you have done this, this union array will be the union array of 2 sorted arrays, and this will also be in sorted order. Why? Because you're using something like set. If you're using something like if you're using C++, do not use unordered set, because if you use unordered set, the ordering will get distorted, and if the ordering gets distorted, you will not be able to maintain the sorted order. Got it? That's why you have to use something like a set data structure. Got it? So if I have to write the brute force approach, it's going to be very simple. We kind of define the set data structure, and then what we do is we go across the first array, assuming that to have a size n1. We can go across the first array and we can say set dot insert, and we can say array of I, assuming the first array a1 of I, and then we can go across the next one, which is from 0 to n2, and we can say set dot insert a2 dot I, a2i. So what this will do is this will put everything into the set. Once you've done this, you can declare the union to be of set dot size. Quite simple again. And in this, what you can do is just iterate. Again, you can use an auto iterator. You can iterate in the set. And once you're iterating in the set, you can say, hey, listen, maybe you can keep a pointer like I equal to 0. And you can say union I plus plus equal to it. So first time goes to the first 0th index, then to the second index. If you're using something like a list or a vector, you can simply write union dot add or push back, in that case it, and this will add it directly. You don't have to maintain an index. So this is how the step 2 looks like. Now if I have to discuss the time complexity of this particular brute force approach, what will it be? Can I say this takes big O of n1 log n1, not n1 log n, where n is the size of the set. So n1 log n. And over here, can I say that the complexity will be n2 log n, again n log n, where n is the size of the set, which will be varying at every step. So you cannot precisely say that logarithmic of something. You cannot precisely determine the complexity for a set. Got it? And now, for this, it's a big O of n1 plus n2 at the worst case. Imagine the array 1 contains all different elements than array 2. Then it will be everything different, and all different will go into the set. And if all different go into the set, it will be n1 over here, n2 over here. So the total elements in the set will be n1 plus n2 if every element is unique. So can I say the time complexity stands at, for the first insertion, n log n, for the second n2 log n, and then a big O of n1 plus n2 at the worst case. And the space complexity is we're using an external set, which might end up taking n1 plus n2 at the worst case if all of them are unique. And then we are using a union array in order to return the answer. Again, this is not used to solve the problem. This is used to return the answer. Please specifically mention that to the interviewer, that this n1 plus n2 space is used to return the answer. I'm not using in order to solve the problem. I'm just using it in order to return the answer. Got it? This will be the time complexity and space complexity of the brute force approach. So if you want to submit the brute force solution, again, the problem link will be in the description. Make sure to add #include bits/std, because in this function snippet, it was not there. And this is how the code will look like. In case you want the Java and Python code, there will be links in the description for the notes. You can go over there and check it out. So we are done with the brute force approach. Now I will be moving to the optimal approach, and we will be taking advantage of the fact that both the arrays are sorted, and we will be using something like a two-pointer approach. It's a very easy approach. So what I will do is I will keep an I pointer over here. I will keep a J pointer over here. So I'll just erase these couple of lines. Yeah, perfect. So I'll keep an I pointer on the first element of the first array, and I'll keep a J pointer on the first element of the second array. And now I will declare a union list. And initially, remember, the list will be empty. It will have a size 0. It doesn't have any elements initially. And now I will be like, okay, I'm over here and I'm over here. If you have to look at the union array, the first element of the union array will be the smallest one, So if I have to take the smallest one, who among it is the smaller one? Obviously 1. So what I'll do is I'll take the 1 into the union array and I'll move the I pointer to the next index. Now, if I have to again take something into the union array, I'll definitely take 1 because it's still smaller than 2. But I say, wait, the last element I took into the union array was 1. And union means no repetition, just unique elements. Like, fine, the last one was 1, so I would not take it. And I'm like, okay, I have a 2. So the next element I have to take will be 2. So I can take 2 from either. So I'll take just 2 from the first. And this 2 was not equivalent to this, so I took it. And now I'll move the I. Now if I have to again take between 3 and between 2, I'll actually take 2 because union always takes smaller, which is at the front. But this 2 is already here. So the last element is equivalent. So I'll not take it. But I will move the pointer. Because it won't be taken because it's already there. So I'll just move the pointer. Correct? Next, I'll compare 3 and 3. I can take any one. So I'll just take the 3. I'll move the pointer. Next, 4 and 3. But wait, this 3 is already here. Do not take it. Move the pointer. 4 and 4. Again take 1 and 4. And move the pointer. This time, 5 and 4. 4 is already there because the last one is there. So move it. 4 is already there. So move it. This time, compare 5 and 5. Same. Take any one of them. And move the pointer. Next, it's over. Please focus. The iteration on one of the arrays is over. If the iteration on one of the arrays is over, what you will do is, you will just say, okay, 5, you're already there. 6, you're not there. Go. So if iteration on one of the arrays is over, you'll not compare anymore, but you will iterate in the remaining portion of the other array. And you will check if it's equivalent to back or not, and then you will keep on inserting into the union. So once it's done, you will have your union array ready, and this will be your answer. Got it? Let's code the optimal solution. Again, the problem link will be in the description. So we are given this function sorted array where we have to return a list, and we're given a couple of arrays, right? So at first I'll do one thing. I'll just figure out the size of the first array, which is something like this. And I'll also figure out the size of the second array, which is something like this. And now I know I'll have 2 pointers. I, which will be pointing to the first index of the first array, and J, which will be pointing. And then we will also have a list, which will be the answer, okay, which is union array. And then at the end of the day, we will be returning this particular list. This is something we do. Now let's say we are comparing both. We'll be comparing till both pointers are pointing somewhere, which means we'll be comparing it till either I is lesser than n1 in the first array and j is lesser than n2, which means both of them are still somewhere in both the arrays. And we say, hey, listen, on the first array, if that's smaller than the second array, both the pointers are pointing somewhere. If the first element is smaller than the other element in the other array, then I say, okay, I'll take this. But before taking, I need to have a comparison. If you remember, when we are taking this one, the union array already had a 1. So you did not take it, right? So I'll be like, I need to compare. So I'll be like, okay, let's take union array. What's your last element? It's like back. Is this not equivalent to the current array of I? If this is not, okay, cool. Let's take it. We're like, fine, I'll take it. No problem. And irrespective of whether you take it or you do not take it, you will move. Because if you take it, it's fine. If you do not take it, that means that element is equivalent to something which is inside union array. So you will not be considering that element anymore. So you move. But if you're doing a dot back, the union array has to have something. What if I come to a case where this is for the first time and the union array is empty? Then you always take the one if the union array is empty because it's the first time. If it's the first time, which means union array dot size is equal to 0, then you always take it. So if the size is 0, it means it's for the first time. You just take it. And similarly, you go to the else, which means the other element is the smaller. The other element in the B array is smaller. If that's the case, cool. I'll just copy paste the same thing. Maybe I'll just copy paste the same thing. I'll copy paste the same thing and I'll say should not be equal to B of J. Should not be. And if it is not, then I'll just push in B of J. I'll just push in B of J. Once this is done, I'll just move the J pointer. Quite same. And after this is completed, I will return. But wait, what if while iterating, this got exhausted? The first array got exhausted. So there must be someone left. If you remember our case, we completed the iteration and there were still 2 elements left. What do you? That means J will be somewhere here. So you need to iterate for these remaining elements. So write it. So you say, okay, listen, if the first was exhausted, J will still be there. And if J is still there, let's do the same thing. I'll say, hey, listen, I'll do the same thing. Which means, okay, fine. If you're not equivalent, go in and just keep on moving. And what if the second got exhausted? So I will still be there. There is someone still in the first. And if there is someone still in the first, you simply take it without any thinking. Yes, without any thinking, you simply take it. And once you've done this, you can return it. So this is the remaining arrays that you just iterate through. Once you've done this, you can go ahead and really let's submit. I'm sure that I write error-free code. Oh yeah, I do. So at one go, I've submitted this code, and this is exactly how it will look like. Now, if I have to ask you the time complexity of this particular code, what will be the time complexity of this particular code? Can I say I'm iterating in some way throughout this entire, somewhere I'm iterating throughout this entire, and somewhere I'm also iterating throughout this entire array. Because no matter what we do, we will iterate through every element. No matter what we do, we will be iterating through every element. Do we do anything apart from this? Yeah, we definitely enter that into the union array. But do we iterate or do we do any for loops or any loops apart from this? No. Steps will always be like this. You'll be either here, either here, either here, either here, either here, either here, either here. So that means it will be O of n1 plus n2. Yeah, there are a lot of loops, a lot of these. But at the end of the day, if you think carefully, you'll actually be visiting every element once. So n1 plus n2 is the time complexity. And space, you can say, I'm just using n1 plus n2 as the worst case if all the elements are unique. And that is for returning the answer, not for solving. Not in my algorithm. I'm using that to return. Tell that specifically to the interviewer. And that's how your optimal solution will look like in order to union two sorted arrays. So what I can say is, I'll go back to the sheet. The union is done. Now it's time to understand the intersection of two sorted arrays. So what does the problem statement state? Intersection of two sorted arrays. Again, the term sorted is very important if you want to go for the optimal solution. So keep that in mind. Okay, what do you mean by intersection? The element that is present in both arrays. Remember this. Present in both. So if I have to write the intersection of A and B sorted arrays, so if I see 1, I don't see a 1 here, so I will not take it. If I see 2, I actually see a 2 over here. So there has to be a corresponding match. So I see a 2 over here, so I'll take it. If I see again 2, there is no corresponding, there is a 2, but this 2 has already been occupied, like is already been matched with this, so there is no corresponding 2 for this, so I do not take it. If I see 3, For this 3, I can say I have a corresponding 3. So I'll take it. Now for this 3, I have another corresponding 3. So I'll again take it. Remember over here, repetition of elements is allowed because you are seeing present in both. Next, 4, no one. 5, yes, there is a corresponding 5. 6, there is a corresponding 6 as well. So this will be your intersection array, right? So if this question comes up in an interview, the first solution will definitely be a brute force solution. And what will be the brute force solution? We are saying that for every element, there should be a corresponding element. For a 2, there should be another 2. For this 2, there is no another 2, so we do not take it. So we just take 1, 2. So for every element, there has to be a corresponding element in the other array. We'll just follow the same process. We will say, okay, fine. We'll pick up 1 and we will check if there's a 1. If there is, we will take it. We will pick up 2 and we will check if there is a 2. And we say we have a 2, so we take this 2. Then we will say, we will pick up this 2 and we will see if there is a 2. There is, but this has been taken by this, so we won't take it. So it's like picking up one element and checking, but at the same time, keeping a track if someone has been used previously or not. So what I do is, I have to keep a track if someone has been used previously or not. So what I will do is, I'll probably create a visited array. Which will be marked as 0, 0, 0, 0, 0, which means they haven't been used. They haven't been used as of now. And now what I'll do is, I'll start with the first element in the first array. You can also start with the first element in the second array as well. But I'll start with the first element in the first array. And I'll say 1, are you here? Are you here? Are you here? I'll just go through the entire B array and I will not find a 1. So if I do not find a 1, I will end up not taking this into my intersection array and I will move forward. Next, 2. Are you here? Yes, I am here. So I'll take this 2. The moment I take this 2, I will mark it as visited. I'll say this 2 has been taken by someone. This 2 has been taken by someone. Fine. We have 1, 2 who found its corresponding 2 in the other array. Now I'll move ahead. When I move ahead, I have a 2. And I'll see for a 2. I see a 2, but it's taken. Now I see a 3. So since it's a sorted array, I am sure that beyond this, there will be no 2. So I stop. I'll be like, I did not find. Next 3. Let's check. 2, no. 3, yes. Yes. Let's take 3. And at the same time, say, you are taken. You are taken. Let's go ahead. 3. Again. 2. Again, 2. No, not equal to 3. 3, yes, equivalent. But, taken. This guy is already committed. So I'll not take him. Next. Oh, he's not committed. And that's 3. So let's take this 3. And mark it as 1. Next, 4. Now when we have 4, do we have a 4, 4, 4, 4? No. Do we need to check for the next? No, it's a sorted array. So if 5, like till 5 you did not get it, beyond that everything will be greater than 5. So no need to check it. Next, 5. 5 you'll get it here. So you'll take 5 and you'll mark it. 6. 6 you'll get it here. So you'll take it and mark it. And the iteration is over. Once the iteration is over, you will have your answer array. Yes, you will have your answer array. And once you have your answer array, that will be the brute force method. Got it? So if I have to write the pseudocode, what I'll do is, I will say n1 is the size of the A array, n2 is the size of the B array. And I'll probably keep a visited of size n2. And I'll mark every one of them as 0. Once I've done this, I will try picking up one element from the first array always. And for that one element, remember we have an answer intersection which we have to fill. For that one element, I will go through J and I'll go through the second array. Now what am I doing? I'm saying, okay, I is 0, which means I is standing here and I'm moving across the entire array. That is what I'm doing, right? So I will be like, okay, if array of I is equal to array of bj, if it is, that means for this A of I, we find a corresponding in the B array. And if we find it, we can take it. But wait, has it been taken previously? And this is where the visited array will tell me the visited of the jth index. So this is the indexing of the jth index. Are you not taken? Oh, you're not taken. Perfect. Please come to our answer. So this will be the corresponding added. So I'll say visited of J has been taken. So please mark it. And you can break out. There's no need to do any further. You can break out. Once you have done this, perfect. And what's the other thing? If this condition is false, we just move ahead. But be sure if at any moment A of J, if at any moment the array of B and J is greater than array of A of I, we say, okay, we've exceeded. You will never find, even if you go ahead. So this will kind of truncate this loop. Just in case you are getting someone greater, there's no point in going forward. There's no point in looping. So you stop. And you can just stop it here. So for every I, you will loop through the entire array B and you'll try to find someone same and which is not taken. If it is not, then you kind of add it to your answer and mark it as taken and you break out. So you keep on doing for every I, and at the end of the day, you will have your answer array. So if I have to determine the time complexity of this brute force approach, what will it be? Obviously, 2 loops running. So that's an N1 cross N2 at the worst case if the break and all these things never happen. At the worst case, N1 cross N2. And what is the space complexity? Obviously, the space complexity is BGO of N2 in this case. Imagine you apply a visited array for this. You can do the reverse as well, where you have a visited for this and you iterate for this and you check for the corresponding in the other array. You can do how you wish to. That is okay. So we can say that in the order in which we apply the algorithm, the space complexity might change. So logically, it will make sense to have the algorithm in such a way that for the smaller array, we have the visited array, so that the space complexity is minimum. But it's okay. This is what you have to tell to the interviewer, that this is my brute force approach. So in case you want to try out the problem, the link will be in the description, and this is how the brute force solution code will look like. But this is something which is taking a lot of time. Yes, this is taking N1 into N2, and that's a lot of time. So we will be trying to optimize this, and let's understand how the optimal solution will look like. So the optimal solution depends on both the arrays being sorted. Since they are sorted, we will be applying something as a 2-pointer approach, and it's going to be very simple. What we do is we basically keep 2 pointers, one at this one and the other one at this. And now we will be taking the intersection of both. So tell me something. If this one, like this is the first case, is not equivalent to this 2, can I definitely say that? We do not have any occurrence of 1. Can I definitely say that? I can. So I'll be like, there's no occurrence of 1. Please move, please. And then I'm like, at 2 and at 2. Like they're equal. Oh, there is an occurrence. There is an occurrence. So I'll be like, let's take 2. And if there is an occurrence, can I say this 2 is for this 2? Right? So I'll move both. Because they matched. Let them put into a relationship. And let's move. Okay. Now, we have 2. I'm like 3. Okay, for this 2, it's lesser than 3. So I definitely cannot have a partner for 2. So I'll be like, not an issue. Let's move. Now this 3 is a partner of this 3. So let's take 3. Let's try to move both. We have tried to move both now. And now this 3 says, okay, fine, I can still have a partner. So again take 3 and move. Now this 4 says, I'm lesser than 5. So I definitely cannot have a partner. Now the 5 says, I'm equivalent to you. So 5 will be a partner. Let's move now both. So whenever they match, move both. If they do not match, then just move. Next, 6, equivalent to 6. So I take 6 and it moves. I run out of partners. Remember this? I've taken 6 and the moment I move both, this I exceeds. So there is no one else to be compared with. There is no one else. So there is no one else who will be partnered with. So it's over. So once you have done both the pointers, this is how it will look like. And this will be your answer. Quite simple. So if I have to code this, the problem link will again be in the description. It's going to be very simple. I is going to be 0. J is going to be 0. And I'll be keeping a vector int answer. And at the end of the day, I will definitely be returning it. And I know one thing for sure. I'll be iterating in both of them. So I lesser than n and j lesser than n. Quite simple. And now I know one thing. if this particular A of I is lesser than B of J, for an example. Obviously, if A is smaller, it doesn't have a partner. Please move. You don't have a partner. Please move. And I'm like, what if it's the other way? The other way means, what if B is smaller? Then definitely the B guy cannot have a partner. Sorry, please move. But if it's not the case, they're equal. You guys can go into a relationship, isn't it? So I'll be like, okay, please go. And both of them are same, so doesn't matter which one you insert. And both of them can go ahead because you guys are committed. Now you cannot have dual relationship. Go ahead and let the other ones find theirs. Fine, I'll go ahead. Once this is done, the answer will be stored here. And that's it. So if I'll just go ahead and submit it. So if I submit it, I will see that this is running. And absolutely fine. Yeah. So what will be the time complexity? Can I say the moment I run out of partners for someone, that's when I end. But what can be the worst case when you like keep on going? Since I'm moving I, I'm moving J. So the worst case can be once this executes, the other time this executes, the other time this, the other time this. So if you're like I, J. So if you're moving like one by one, so it's more like once here, you're here, this moves. In the next step, 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 this moves. So moving one by one. And this one has an N1 length, this one has an N2 length. Can I say the time complexity will be N1 plus N2? That is in the worst case. Can I say the space complexity? Are we using any extra space? The answer to that is I don't think so. We're not using any extra space. So the optimal solution has a time complexity and space complexity of this that is seen on the screen. So I can say that I've successfully solved the optimal solution of intersection of two sorted arrays. So I can go back into the sheet and I can say this is done as well. So with this, we cover up 9 problems from the easy section of the arrays. I know this was a long video and I hope you enjoyed every bit of it. So please do consider giving us a like because I've put up enough effort for this video and you can understand by the voice. So to continue our tradition, if you have understood everything, do comment understood and also make sure you do the assignment. There was an assignment that you have to rotate the array by D places. So make sure you do the assignment and drop the code in the comments. And if you are new to our channel, please do consider subscribing to us. And if you haven't followed me on all my social media handles, LinkedIn, Instagram, Twitter, all the links will be in the description. Do join our Telegram group. With this, I will be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken